Hi, welcome back to College Algebra. In this week 4, we're going to talk about equations of a line, relations, and functions. We'll cover 2.3, 2.5, and 2.6 in our textbook. Again, please look over the slides for these measurable outcomes. Okay, section 2.3, equations of a line. The slope-intercept form of a line is a line that we'll use quite often to describe a line. In the previous lesson, we talked about the standard form of a line, which is ax plus by equal to c, where a and b are not 0. And so let's talk about what the slope-intercept form is. So you remember from last lecture that we talked about how the slope of a line is given by this formula, change in y, which is y2 minus y1, divided by change in x, which is x2 minus x1. So this is the rise over run formula that we discussed. So this is the equation for the slope. And suppose that we have 2 points that we know on a line. One of them is called the y-intercept, which is where x is 0. And so suppose that when x is 0, the y-intercept is at b. Then given any other point on the line, x comma y, we can substitute, we can use this point and also the y-intercept to define our slope. So plug in y into y2, and so y2 is y, y1 is b, and then x2 is x, x1 is 0. You plug it in, you get this equation for the slope. And then x minus 0 is x, and if I cross multiply, I guess mx is equal to y minus b, and if I add b to both sides, I get y is equal to mx plus b, or if I flip it, y is equal to mx plus b. So this is the equation of a line that has the slope m and the y-intercept b. So that's why we call this the y-intercept, the slope-intercept form of a line. So again, here's the picture for this. Again, this is the 0b is the y-intercept, and x comma y is any point on the line. And when we computed the slope, which is m, we also was able to get the equation of the line, because x and y are variables that can change, and if x and y is on this line, then this equation holds, which means that this equation also holds. Okay, so here's the equation of the line in slope-intercept form. Y is equal to mx plus b, where m is the slope and 0 comma b is the y-intercept. So for example, if I have this equation, 3x plus 4y is 4, we can rewrite it in slope-intercept form. So the way we do that is we try to solve for y. So if I subtract 3x on both sides, I get 4y is negative 3x plus 4, divide by 4. If I divide by 4 here, I get y on the left side, which isolate y, and then divide by 4 by both of these. So I get y is equal to negative 3 over 4x plus 1. So the slope is negative 3 over 4, and the y-intercept is 0 comma 1. Okay, how about this equation? Y is equal to negative 3 4 of x plus 1. Well, again, if I plug in the 1 here, tell me the y-intercept, 0 comma 1, and the slope is negative 3 over 4. And so we want to graph this equation. So we look at the slope, which is negative. One way to look at the slope is negative 3 over 4. So rise is negative 3, which means you go down 3. Run is 4, which means you go to the right by 4. And so if I start at the y-intercept 0 comma 1, I can go down 3 and go to the right 4, so I get another point. We can also look at this another way. We can put the negative at the denominator instead of the numerator. And so if we look at the slope as 3 over negative 4, then the rise is 3 and the run is negative 4. So I go up 3 and I go left 4. So again, if I start here, if I go up 3 and I go left 4, I get another point. So by looking at the negatives in two different places, we can get two points on the line. If I connect the dots, then I get the equation of this line. or I get the line, the graph of this line. Okay, we want to know whether these lines are parallel, perpendicular, or neither. So if I look at part A, notice the slope is the same, -2, -2, so that means they're parallel. And they have different y-intercept, but that's fine. These lines are parallel, but they're not the same line because they have different y-intercept. And then for part B, sometimes we might have to solve so that the equation is in the slope-intercept form. So for example, if I divide by 2, I get y is equal to -3/2 x plus b plus 1. And then on this side, if I solve for y by adding 4x and then dividing by 6, I get that the slope is 2/3. So if this is 2/3 and this is -3/2, these are negative reciprocal. We saw last time that means that these lines are perpendicular. And finally, I look at these part C. Again, I can solve for y. The slope is -1. This line is horizontal. We saw in the last week's lecture. So this slope has zero slope. So that means that these two lines they don't is neither. They're neither parallel nor perpendicular. We're going to use the slope-intercept form to find an equation of a line that has slope -3 and pass into this point. So here's the equation: y is mx plus b. So we know m is -3, and we need to find b. So I'll plug in -3 for m. To find b, I can plug in this point 1, -4 into x and y. So x is 1, y is -4. So you plug in -4 for y and 1 for x. I can solve for b, and I get that b is -1. So now I go back and plug in -1 into the b part. So my equation is y is equal to -3x minus 1. Okay, so we use the slope-intercept form of a line to construct an equation of a line given the slope and a known point of the line. But we can also use another equation called the point-slope formula, which if we know a point and a slope, we can also find the equation. And so again, this is the formula we saw earlier for the slope. If I have a point x1, y1 and a slope m, then given any xy on which is another point on the line, then this equation must hold. Y minus y1, x minus x1, changing y over changing x must be m. And now I can cross multiply, so I get m times x minus x1 is equal to y minus y1, because this will cancel. And then I can also move the y1 over to the left side, or if I want, I can also switch. Or I can switch the order of this to get y minus y1 is m x minus x1. So this is called the point-slope formula because it requires one point, x1, y1, and the slope. So here's the point-slope formula. Y minus y1 is equal to m x minus x1, where x1, y1 is a point and m is the slope. Therefore, we have the point-slope form. Okay, let's use this formula to find an equation that has this slope, -3, and goes to this point. So m is -3, and the point is x1, y1 is 1 minus 4. So we plug into this formula, y minus -4 is equal to -3 x minus 1. So you plug it into this point. So y plus 4 is equal to -3 x minus 1. And so there's our equation for the line. Now this question asks for to write this in slope-intercept form, so we have to solve for y. So one way to do this is to clear the parentheses. -3 times x is -3x, -3 times -1 is +3, and then move the 4 over by subtracting 4, and here's my slope-intercept form. But for the most part, in general, if you take pre-calc or calculus, it's okay to leave the answer in either point-slope form or slope-intercept form. Either form would be valid. Okay, so we want to find an equation of a line that passes through these 2 points. So first we need to find the slope, and the slope is given by changing y. 1, for example, I can say 1 minus -1 divided by 3 minus 5. So if I do that, I get 2 over -2, which is -1. So that's the slope. Now we can use the point-slope formula. So y minus y1, m x minus x1. So m is -1, and then x1, y1, I can pick any of these points. It doesn't matter which one. So let's pick, say, this one. So y minus 1 is equal to -1 times x minus 3. And then if I want to put this in slope-intercept form, again, I can clear the parentheses by multiplying this in, and then bring in -1 over to get the slope-intercept form. Okay, let's find an equation of a line that passes through this point and parallel to this line. So we know the point, so we need the slope to get the line. And so one way to find the slope is to solve for the slope-intercept form of this to get the slope. So if I do that, I can subtract -4x. I can minus 4x on both sides to get y is minus 4x plus 8. So the slope is -4. So this line is to be parallel to this line. It must have the same slope. So that means we know the slope of the line we're looking for is also -4, and it has to go to this point. So again, we can plug into the point slope formula. And then -3 for y1, -2 for x1, and then the m is -4. Again, I can clear the parentheses if I want, multiply it in, and then bring the 3 over, and I get this equation for the slope-intercept form. So notice that these two lines are parallel. The black line is the line that is let's see, given originally. So the black line is this one, and the line that we found is the blue line, which is parallel to that line, and then it also passed through that point. So notice we found a line that passed through the point -2, -3, and also parallel to the given line. Okay, find an equation of a line passing through this point and perpendicular to this line. So this is similar to the last problem, except now we have to make sure it's perpendicular. We're going to write the answer in point slope form. So again, solving for y, minus 2x divided by 3. The slope is -2/3. So that means that the slope of the other line must be the negative reciprocal of this. So it must be 3/2. And then since we know that it has to go to this point 4, 3, we plug in 3 into y1, 4 into x1, and then here's the point slope form of the line. So this line right here is perpendicular to the given line up here. Okay, so here's a summary of all the lines that we talked about in this lecture. There's the standard form of a line: ax plus by is c. For example, 2x plus 3y is 6. Horizontal line is given by y is k, where k is the constant. Y is 3, for example, is horizontal line. Slope is 0. Vertical line is x is equal to k, so x is equal to -2 is an example. This is a line that is vertical and has infinite or undefined slope. And then in this lecture, we talked about y is equal to mx plus b, which is the slope-intercept form. We have the slope and also an intercept. And then the point slope formula is where we know the point x1, y1, and also the slope m. And then this point slope formula is actually very easy to work with. It's actually maybe easier than the slope intercept form, because all we have to do is, if we know the slope and a point, we plug it in and we're done. And so, but whereas if you want to find mx plus b, you have to plug it in and you have to solve for b. So sometimes it takes a little bit more work for this form. So the point slope formula is actually a very nice, easy formula to work with. But you should be able to know how to go back and forth between the two. Okay, relations. So a relation is simply a set of ordered pairs, x comma y. If you have a bunch of x and y ordered pairs, then this defines a relation in x and y. And then the first components of the ordered pairs is called the domain. So all the x's is called the domain of the relation, and the set of all y's is called the range of the relation. So for example, here's a set of points, just a bunch of points, and in this case, it kind of links the length of a woman's femur to her height, and so that's a relation between a woman's femur to her height. So the domain would be all the set of all x coordinates, so 45.5, 48.2. So these are all the x coordinates of the relations, and all the y coordinates of the relation forms the range of the relation. A relation can also be a finite number of ordered pairs or an infinite number of ordered pairs. And so let's talk about the different ways we can define a relation. So one way to define a relation to kind of name a set of ordered pairs. If our set is finite, we can just name it. Another way to define a relation is to define a correspondence. So for example, a picture like this, where the domain is on the left side, the range is on the right side, and the relation is a set of all correspondence. So 1, 2, 1, -4, -3, 4, 3, 4. So you look at here, and the arrow tells you the y coordinates of that one point in the relation, and so this relation has 4 points, 4 order pairs. Or a relation can also be defined by a graph. So for example, if I graph all the points in my relation, then that could be a way to define a relation. So again, either a set of order pairs, a correspondence, or a graph. Typically, when we talk about in math, we usually do graphs because, in fact, relation is a precursor to the next definition, which is a function. And so typically, we graph function by plotting points. So this is kind of a very common way to do it. But certainly, for finite sets, we can also do it by these methods. Okay, and then finally, also a relation can be expressed by an equation. So for example, x is equal to y squared. So the solution to this equation defines an infinite set of order pairs. So the set of all order pairs that satisfy this equation, or the solution set, would constitute the relation. So if I were to graph this equation, I get these are the order pairs. All the points on this graph are all the solution to this equation. So this is a relation. Okay, so we can use interval notation to express the domain and the range of this relation. So for example, the domain of this relation is all the x coordinates. If you look at all the points in the relation, which is this oval, and look at the x coordinates. So that means it is in this interval. So the x coordinates is from -8 to 8. So that's the domain. And then the y coordinates of all the points is from -5 to +5. And for part B, we can look at the again the domain is set of all x coordinates. So notice that because this goes forever, the set of all x coordinates of all these points is from 0 to infinity. So that means you can go from 0 to infinity. Notice 0 has a square bracket including 0, but we usually use open because we're not including infinity because it's not a number. The ranges are the y coordinates of all these points. So the range starts from here, which is 2, but not including it because -2, not including this -2, but all the y coordinates goes all the way up to a positive infinity. So the range is from -2 to infinity, not including -2. So again, the domain is set of all x coordinates. The range is set of all y coordinates of the relation. Okay, functions. Functions is actually what we mostly study in math. So relation is just one step to this. So what is a function? So if I have a relation in x and y, then y is a function of x if for each element x in the domain there's exactly one value of y in the range. So a function is a relation, but not every relation is a function. So what this means is that if we had a set of order pairs that forms a relation, right? Again, a relation is just a set of order pairs, no extra condition on it. But for that set of order pairs to be a function, we need to have that no two order pairs have the same first coordinate and different second coordinates. So let's kind of see some example of this. So how do I know whether a relation is a function? So for example, let's look at this. So these are relations for sure. But if I look at A, is this a function? Does that mean is y a function of x? So what that means is that every x coordinate must have exactly one y coordinate. But notice in here, the x coordinate 1 here has actually correspond to 2 y's. So therefore, it's not a function. So again, a function is that for each element x in the domain, there's exactly one value in y in the range. So this x has multiple y so that means it's not a function. For every x on here in the domain, there's exactly one y, so this is a function. This relation defines a function. And same thing here. This looks like everything gets correspond to 4, but that's okay. Every x has exactly one y, which is 4. This x has one y, which is 4. Notice in this first case, this x has two y's, right? 3 and 4. That makes it not be a function, but b and c are both function. So again, another way to see this is if you plot the order pairs, these two x's are the same, but they have different y's, and so that's not a function. And again, if I write the order pairs, notice every x have a different there's no x that has two y's, right? So different x give you different y's here, and so we don't have any x coordinate that has two different y's. Again, if I write it down, I get that there's no x coordinate that has two different y's. Okay, so another way to figure out whether something is a function is to use the vertical line test. So if I were to graph the set of all points in the relation, then y is a function of x if no vertical line intersects the graph in more than one point. So for example, if I were to draw vertical lines, if I can find one line that intersects the graph at more than one point, for example this line, then that means it's not a function. So again, if I have at least one line that intersect the graph at 2 points, then it's not a function, because that means that x value has two different y values. This one, regardless of how you draw vertical lines, there's no vertical lines that meets the graph at more than 1 point. Every vertical line meets the graph at exactly one point. If you have one or less, then that'll be a function. Okay, so the question is, why do we have this definition? Why is it that we don't want multiple one x to have multiple y's? Well, it's because we want to define phenomenon in nature that really follows this definition. So for example, we want to model things like temperature. So let's say that I have a function, I want to describe a temperature as a function of time. So that means the x coordinate is to say temperature, and the y coordinate is the x coordinate is time, and the y coordinate is temperature. The reason why we don't want to call this a function is because this says that at some given time there's two temperature, and that doesn't make sense. So we only want at any given time to have one temperature. So that's why we have this restriction on function, is that we don't want one input to have two different outputs. So this could be a map of time versus temperature, because at any given time there's only one temperature, for example. So here's the function notation. We use this f of x notation. So f is the name of the function, x is the input, and then 2x is the output. So f of x is also the y value corresponding to x. So we call this f of x, or the value of the function f at x. So for example, f of x is 2x. This is the function. If I say f of 5, I can plug 5 into the function to get 10. So 5 is the input and 10 is the output. So that means that the order pair 5, 10, right? X is 5, y is 10, is an order pair for this function. So we can say f of 5 is 10. That's one way to read this. F at 5 is 10, or f evaluated at 5 is 10. Different ways to say the same thing. Okay, suppose you have this function. How do you evaluate? So this is called function notation. G of 0 means you plug 0 into x. If I do that, plug 0 into x, I get -1. So g of 0 is -1. So that means that 0, -1 is an order pair for the function. G of 2, again I plug in 2 and I evaluate. So I get 1 minus 1 is 0. So g of 2 is 0. And g of 4, plug in 4, I get 1. So g of 4 is 1. So g of 4 again is 1. So if the input is 4, the output is 1. So the order pair is 4, 1. So x is the input, y is the output. Same thing here. You plug in -2, I get -2. So g of -2 is -2. So notice that these inputs give you the corresponding order pairs. And if I were to plot it, we notice that you get a straight line. And that makes sense because this function is a linear function that we saw earlier. It has slope 1/2 and has y-intercept -1. So this is a linear function. So it's a special example of function. Okay, let's do some more function evaluation. Well, if f is this function, x squared minus 2x, and g is 3x plus 5, what is f of t? Well, f of t means that you just plug in t for where x is. So whenever you see an x, you plug in t. So the function f of t is t squared minus 2t. Okay, how about g? If g of x is 3x plus 5, what is g of w plus 4? So again, this w plus 4 is just the input. So you take this whole input, you substitute in wherever you see the x. So 3 times x means 3 times w plus 4 plus 5. So evaluate the parentheses by multiplying 3 times w, 3 times 4 is 12, plus 5, 3w plus 17. So g of w plus 4 is 3w plus 17. And finally, f of negative t, mean you take the input and you plug in where you see the x. So negative t, quantity being square, minus 2 times negative t, so you have t squared plus 2t. So simplify. Okay, so again, if I would look at the graph, h of negative 1, right, the way we interpret that is that when the input is negative 1, what's the output? So here's the graph of it. When x is negative 1, the output is 2. So that means that h of negative 1 is 2. So again, this is the input, negative 1. This is the output. So the order pair is negative 1, comma 2. H of 2, same thing. That means the input is 2, and the output is going to be, based on the picture here, is 1. So h of 2 is 1. How about h of 5? Again, look at 5. Here's 5. The output here is an open circle. That means that there's no output. So h of 5 is undefined. H of 5 is not defined. How about this one? This one is what value of x is h of x is 3. So again, x is the input, h of x is the output. So we're saying what x value has output 3. So the output means the y value. So let's look at 3. Look at the horizontal at 3. Where does the graph hit this line? Well, right here. So what x gives you that the output is 3? Well, this x, negative 4. So to solve, basically, if I want to solve this equation for x, then from the graph, that the solution x is negative 4. So again, h of x is 3 means that x is negative 4. And finally, for what value of x is h of x is 0. So again, h of x is the output is 0. So that means I look at the y value. The y value is the output. Here's 0. So for what value of x is the y value 0? Well, there's two places. One at negative 3 and one at 4. So this equation has two solutions, negative 3 and 4. Okay, so that's that example. And so let's look at the domain and range of functions. This is very similar to relation. Look for x coordinates. And so if you have a function that's given by a formula, things that we want to keep in mind is that the domain of the function will exclude values of x that make the denominator of a fraction being 0, and also it exclude the value of x that makes the expression within a square root negative, because you can't divide by 0 and you can't take the square root of negative. Those x value that makes the denominator 0, or the expression inside the square root negative, values that has no output, because we can't perform those operations. So for example, what's the domain of this interval? Well, again, this function, you have the division. You cannot divide by 0, so whatever makes this 0 would not be in the domain. So when is this 0? Well, this is 0 when x is 1/2. 2x minus 1 is 0 when x is 1/2. So 1/2 is not in the domain. So you exclude 1/2 from the domain. So that means that the domain is from negative infinity to 1/2, not including the 1/2, and then from 1/2, not including 1/2, to infinity. So every number except for 1/2. So that would be the domain. Everything is okay except for 1/2. What's the domain of this? Again, you have a fraction. That means the bottom cannot be 0. But notice that x squared is positive, right? It was at least non-negative. So non-negative. So meaning that x squared is 0 or bigger. If something is 0 or bigger plus 9, the bottom is always bigger than 0, strictly bigger than 0. That means this thing is never 0, and so that means that this function would never have a 0 denominator. That means that the domain is all real numbers. So there's no restriction, because there's nothing that makes the bottom 0. So So hopefully that's okay. Yeah, again, the bottom is being positive means that it will never be 0, which means that there's no bad points. There's no x value that makes this division a divide by 0 problem, and so therefore all real numbers is valid for this function. Therefore the domain is all real numbers. Okay, here's the square root. So again, the restriction here is that you cannot have a square root of negative numbers. So we want to make sure that this expression is non-negative. So that means you want t plus 4 is bigger than or equal to 0, because you cannot have this being negative, because then you cannot take a root of a negative numbers. So t plus 4 has to be bigger than or equal to 0. That means t has to be at least -4. You move the 4 over. So the domain is from -4 to infinity, including -4. And then this function t squared minus 3t, there's no restriction here. Any input will work, so the domain is all real numbers. So -infinity to infinity. Okay, that's all for this week. Thanks for watching.